a trailer moving on the road, it is moving with much more force than a small car moving at the same speed. So basically, that property of objects that depends on their mass and their velocity is known as their momentum. So basically, what is known as the momentum of a body is defined as the product of its mass and its velocity, and the unit is kilogram meter per second. So the momentum is equal to the product of mass and velocity, that's mv. Impulse is another quantity that is related to momentum. It is the product of the average force acting on the particle and the time during which the force acts. So the formula for impulse is given as F times T, where F is the force and T is the time. And the unit of the impulse is the Newton second. So impulse is a vector and it has the same direction as the direction of the force. So basically, if you have a force moving from left to right, the impulse of that force is also moving from left to right. To demonstrate the concept we've been talking about some questions, the first question is, we are told that a stationary ball is hit by your average force of 15 Newton for a time of 0.03 seconds. What is the impulse experienced by the body? So in this case, we have the impulse is given as the product of the force and the time. So basically, that would be the force, which is 15 Newton times the time of 0.03 seconds. And that would give us 1.5 Newton second. That's the impulse. Secondly, in this question, we have a body of mass 3 kg moves with a velocity of um of 10 meter per second. Calculate the momentum of the body. This is quite easily done. All you need to do is just look for the product of the mass, which is 3 kg, and the velocity, which is 10 meter per second. That's 30 kilogram meter per second. So these are the calculations involving momentum and impulse. We have the Newton's law. There are three in number. We are going to be talking about them in this section of the video. Now, the Newton's first law states that every body continues in a state of rest or of uniform motion in a straight line unless acted upon by an external force. So what this means is that if you have a ball moving in a straight line, it will keep moving until you stop it. Or if you have a body moving at rest, not moving, it will keep being at rest until you move it out of its position. So in the first case of being at rest, it is very obvious, because if you keep a ball on the floor at rest, unless the wind blows hard or unless you kick it, it's going to remain there. But the other concept of motion, if a body is in constant motion, it will keep in that constant motion until it's acted upon by force. That is not very practical now. It's not very practical and realistic, because when we have objects in motion, they are automatically acted by a force known as friction. So because of that, when we have objects moving in constant velocity, they tend to slow down after some time because of the friction that is naturally present in our natural environment. In Newton's second law of motion, we have that the second law of motion states that the rate of change of momentum is proportional to the impressed force and takes place in the direction of that force. Now, Newton's law of motion is a special motion law because it's a relationship between um, the statements, and it also has a mathematical representation. For us to understand the second law of motion, we have to understand the relationship between the force of the body and the acceleration. So in this case, we have that the force is proportional to the mass and the momentum, because if you recall, the momentum is given by the change in velocity divided by rather the acceleration, the force, the product of the mass and the acceleration. So the acceleration is equal to the change in velocity with time. So here we have force proportional to mass times acceleration, and then we have the force equals to kma, where k is a constant. Now the unit of force is chosen so that k is equals to 1. Hence, we can write that F equals ma. So this is the statement of the second law, and it also obeys this Newton's second law of motion, because the rate of change of momentum is proportional to the impressed force and takes place in the direction of the force. So this is how it works. Let's talk about Newton's third law of motion, and this law states that the action and reaction are equal and opposite, or you can also put it this way: to every action there is an equal and opposite reaction. Now, this third law of motion is actually the simplest. Apparently, is the simplest, but it is actually it is actually deceptively difficult to grasp for many people. We also often struggle with the concept, because and it happens in everyday life. It is very practical, but at the same time, it is surprisingly difficult for people to grasp. So before we move on, try to take in the concept of everything that happens. Basically, anytime you try to move forward, you are also pushing backwards on the floor. So because you push backward on the floor gives you a forward force. So you can see that there's to a forward force, there's a backward force. To an upward force, there's a downward force. So that means in the universe, every action and reaction, they are equal and opposite. In a related concept, we have the conservation of momentum. And this conservation of momentum, it is a simple law that is also practical, is as practical and related to the Newton's third law of motion. And it says that in a system of colliding particles, the total momentum is always conserved, provided that there is no net external force acting on the system. So in this case, what this means is that when you have a closed system, the amount of work done on the system is equal to the amount of work done by the system. That means there's no net change in work, no net change in heat. And in this case, it is called a closed system because heat and as a result work different types of work. You can say example of work like heat, potential energy, and all the rest. None of that is affecting the system. That means the heat content of the system is not changing. The heat content is of system is static. So this is kind of related to a thermodynamics system. We'll be dealing with thermodynamics later on, but concept of conservation of momentum is needed for us to understand linear momentum. Now, because of the concept of conservation of momentum, we have this equation which expresses this relationship, and this states that you can see the equation here. We have MAUA plus MBUB equals MAVA plus MBVB. Now, the term MAUA is the term of initial momentum of the first object. The second term is the initial momentum of the second object. Now, the third term, that is the first term on the right hand side, is the final momentum of the first object, and then the second or the last term is the final momentum of the second object. So this involves two colliding bodies. Anytime you have two objects in collision, there's a conservation of momentum of the final and initial states. So we've already defined momentum as mass times velocity. That means the total momentum before impact is equal to the total momentum after the impact of the collision. Some moments ago, we talked about the fact that action and reaction and equal are opposites, right? Now, basically, this is a practical application of that because, as you can see in this gun, when you fire a gun, from the moment you fire a trigger, that the bullet begins to move forward. That is the action, and then immediately the opposite and equal reaction, which the gun jerks backward. Now, this is obvious if you've ever operated a gun or basically anything that moves. You know that when you have uh, a forward force, it will be accompanied by corresponding backward force. This is the application of Newton's third law of motion, and it is called the recoil of a gun. Let's talk about an example to wrap up this video. And this example is a practical example of rockets and spacecraft. You are told that a rocket is burning fuel at the rate of 200 grams per second and ejecting all the gas in one direction at the rate of 400 meters per second. What is the maximum weight of the rocket what is the maximum weight that the rocket can have if it is going to move vertically upwards? Now, basically, in this case, this is basically based on a system where the mass is leaving the system. Now, in this case, we can work on different equation. There's a particular equation we can use. When we use that equation, it simplifies this whole process, but I don't want to make these things complex with that equation. We're just going to make use of a practical solution. So here we have the mass of the gas per second is 200 over 1000. That's kilogram per second. We've converted from gram per second to kilogram per second by divided by 1000. That is similar to the conversion factor. Then next, the velocity of the expulsion is 400 meters per second. So when we multiply the momentum, when we multiply the mass and the velocity, we get the momentum. That's 200 over 1000 times 400. So at the end of the day, we have from Newton's second law of motion, we have that the weight equals 200 over 1000 times 400 Newton. That's 80 Newton. So basically, this is the momentum change per second, and that is equal to the force. So the force is equal to the weight, which is 80 Newton. So this is a practical demonstration of Newton's second law of motion, and that that rounds up the topic of linear momentum. Now we've come to the end of this episode, and I thank you for watching to this extent. Now, as a final tip, I'll give these questions for you to solve. So you can solve this question. You can also send the answers to the number in the description of this video. So thank you for watching, and I promise in another episode I will be dealing with the solution of questions like this that I've been giving you guys in this series.